The following program is brought to you by Caltech.
Good evening, ladies and gentlemen. I am Aris Rozakis. I am the chair of the Division of Engineering and Applied Science here at Caltech, and I would like to welcome all of you this evening to the Earnest C. Watson lecture series. Before I introduce our speaker for tonight, I would like to tell you that our next event will take place on December 5th, on a Wednesday, again, and it will be a lecture given by Professor Viviana Gardinaro from the Division of Biology, and her talk is entitled Brain Control with Light. Well, tonight, it is my great pleasure to introduce our speaker, Professor José Andrade, Associate Professor of Civil and Mechanical Engineering here at Caltech. José received his Bachelor's of Science degrees in civil engineering from Florida Institute of Technology, and his MS and PhD degrees in civil engineering with a focus on geomechanics from Stanford University. José joined Caltech in 2010 after 4 years at Northwestern University, where he was an assistant professor of theoretical and applied mechanics. As a matter of fact, it was during one of my visits to Northwestern where I first met him and persuaded him to leave the icy winters of Chicago and come to sunny California. Being a true Ecuadorian, both the climate as well as the earthquakes of California appealed to him greatly, so he made the jump. Unfortunately, since 2010, we haven't had a very serious earthquake event for him to enjoy. So José is the recipient of several honors and awards, including the Zinkevich Medal in Computational Mechanics, one of the top awards in that field, given by the Institute of Civil Engineering of London, the National Science Foundation Career Award, the Young Investigator Award from the US Air Force Office of Scientific Research, the American Society of Civil Engineers Casagrande Award, and the Dr. Vicente Rocafuerte Medal for Scientific and Research Accomplishments from the National Assembly of the Republic of Ecuador. Professor Andrade's research objectives are to develop a fundamental understanding of the multi-scale and multi-physical behavior of a class of materials that we call porous materials, with special applications to geological materials, for example, soils and rocks, as well as engineered porous materials, engineered infrastructure materials, such as cements. What makes his work unique is the imaginative combination of computational, analytical, and experimental techniques, all working together to obtain unprecedented insight into the mechanics and physics of granular solids. He is trying to unravel what makes geological materials tick at very large length scales. However, in order to understand the massive landslides and the large earthquakes which devastate entire cities, one has to start at a very minute scale, or to first learn to see the world in a grain of sand. So José has not limited his study to granular materials to the Earth. He has also been studying the interaction of our JPL rover wheels with Martian soil. It is great for me to see him follow in the footsteps of another Caltech civil engineer, Professor Ron Scott, a great friend of mine, who was the first man to dig in the moon. Perhaps José is getting ready soon to be digging on Mars. Actually, I know so, that in a mission that will be launched in 2016, he is playing a key role in the digging part. So please join me in welcoming Professor José Andrade to the stage to give his lecture entitled Seeing the World in a Grain of Sand.
Thank you, guys. Thank you. Well, thank you for that very kind introduction, Ernest. I think it's all downhill from now. It's a pleasure for me to be here and give this Watson lecture. Welcome. And my objective here is to tell you a little bit about granular materials and the kind of work we do, but also to have a good time. So let's have a good time. And let's start by telling you who really does the work here that you're going to see, and that is my group. This is a group of people that I have the privilege to work with. These are my PhD students and postdocs, and everything you see today is a result of their effort. So it's really about their work that you're going to be learning tonight. And this is the kind of work we do in our group. This is actually the beginning of science. And actually, this is the roadmap for this Watson lecture tonight, believe it or not. This is how it was born. So this is the humble beginning of science and a Watson lecture. So today we're here to talk about granular materials and have a good time with them. We're going to play with sand, essentially. And before we do that, we need to define what we mean by a granular material. So what are these granular materials? So I'm going to give you some definitions. The simplest one, perhaps, is that they're made up of small particles. Okay, so we all know that. Sugar is a very good example of a granular material. Then we go deeper and we realize that these are materials that don't behave exactly as a solid or as a fluid. They're somewhere in between. They have a behavioral problem. They kind of go back and forth. They're non-everything. They're non-linear, non-elastic, non-homogeneous, non-isotropic, and therefore non-easy to model. This actually comes from our own Paul Jennings here at Caltech, so I like that quote. And my favorite one is about sand. And I don't like sand. It's coarse, it's rough, and it gets everywhere. That's from Anakin Skywalker's Star Wars. All right, so we have a definition now for what granular materials are, and we're going to be playing with these materials and understanding, what makes them tick, as Ari said, from a small scale, and then we're going to take it all the way to the engineering scale. So this is the outline of my talk in cartoons. We're going to start by looking at the phenomena that these materials display. They have a very interesting way of behaving that is very different from many other materials. Then we're going to get into the paradigms that we use as engineers and scientists to understand these materials and to also model them, because our intention here is really to predict their behavior. That's what it's all about. And then we're going to apply this knowledge, these tools that we develop under the paradigms, in some applications that are of interest to us as humans. So let's start with the phenomena. Let's start with the fun part, okay, and show you the interesting things that these materials do. The first example comes from the so-called force chains. This is a video of an array of granular materials. These are called photoelastic disks. These are small disks of photoelastic material, and they shine when they're under load. So each one of these little disks is shining because load is being applied to them. Now, at the bottom of this specimen, pressure is being applied in a very homogeneous way, so very constant pressure. Yet you see that the force transmission through this granular material is very non-uniform. Even though the boundary loading is very uniform, the transmission throughout the array is not. Okay? So they form these so-called force chains, or these paths, that force the sites to take. And the question, and what makes people wonder, physicists especially, is why does a force decide to take a certain path? Why didn't it take another path? What makes this force chain special? Okay? And you don't see this kind of behavior, say, in metals or in rubbers. So this makes granular materials very interesting right from the get-go. Remember this definition of non-homogeneity and non-isotropy. Another type of phenomenon that we're very used to seeing everybody has walked, I hope you've walked on the beach, and you've seen this phenomenon of this dry front, right in front of your foot as you're walking, right? So you can see it here, right, that the sand right in front of a foot is getting a little drier than the rest of the sand, right? So this sand is very wet, and as he's stepping down, he's drying the sand in front of him. Why does that happen, right? We know that it happens. Why does it happen? The reason why it happens is due to a very interesting property of granular materials that is called dilatancy. And dilatancy is the ability of these materials to expand as they're trying to deform. So as you're walking on sand, you're deforming the sand, and the sand wants to expand, and because it wants to expand, it dries. So the sand loses some of the water it holds in between the pores. So this is a very unique, again, behavior of these materials that you don't see in any other engineering or engineered or natural materials. So remember dilatancy. So dilatancy and force chains occur, but then as we add moisture in between the pores, we get a very different response. So again, we all have experience with building sandcastles. So you know that if the sand is too dry, it doesn't work. Sand is too wet, it doesn't work either. My daughter knows this. The sand has to have just the perfect moisture for the sandcastle to hold, right? To be able to create this beautiful structure, you need to have what's called capillary forces, right? And this is due to, again, partial saturation, some moisture in between the grains that actually makes this structure hold. So moisture or water in between the pores in these materials makes a huge difference in the mechanical behavior of the structure, okay? So unlike many other materials, water or the presence of fluids changes the whole game, okay? So speaking of, I'm actually gonna kill the volume on this one. Speaking of fluids, this is what's called a fluid-solid or a solid-fluid transition. Watch the impact from that ball, that steel ball, as it goes into an initially solid material, which is sand, and how it splashes and forms this jet, okay? That looks like a fluid. It looks like a water to me. And this is not water, this is not a fluid, this is actually sand. So it starts as solid, it's resting there, nothing is really moving, and then all of a sudden, as the penetrator goes in, this jet comes up at twice the speed, roughly, of the penetrator. So these materials have this amazing ability of going from a very quiet state, from a very solid state, to a very fluid state. And this is a major challenge for people like me to capture this behavior. So we've seen that these granular materials are very different from many other materials in terms of their mechanical behavior. And this is a challenging thing to capture when you're trying to model them. Okay, so we've seen that these materials are cute or interesting, but are they really useful? Do they really matter? What can we do? So let me show you, let me scare you a little bit and show you how important they are. So this is a picture of the 1964 Niigata earthquake in Japan, where there was severe liquefaction, and we're going to learn a little bit about what liquefaction is. These buildings have nothing wrong structurally. They're not broken. The concrete is fine. Everything is fine structurally. What failed here is the foundation of these buildings. These buildings are not able to pass force to the soil from the foundation. Why? Because the soil underwent this so-called solid fluid transition that we saw before. It started behaving as a solid. It was very quiet and robust. And then it became a fluid as a result of this liquefaction phenomenon. Now, what is liquefaction? Remember the influence of water inside the pores. When an earthquake hits, as it did in 1964, it excites the sand. This was sand here in Japan, very close to the ocean. The sand is very wet, is very much saturated with water. When the earthquake hits, it excites the sands want to deform, and because of dilatancy, remember that effect on the beach, The sand wants to contract. It cannot because it has water in the pores. The water in the pores feels this contraction and pressure goes up. When this happens, the material undergoes this transition from a solid state to a fluid state, and nothing can stand on this material, essentially. You have this collapse of these buildings. So let's watch a video of liquefaction as it actually happens in real life, in real time. And this is a video from the latest earthquake in Japan. Watch the cracks as they open and close here. So look at that crack. An earthquake is happening and someone's taping this. You see the crack opening and closing and also ejecting water from below the surface. This is groundwater coming from underneath. All of that water that you see there is coming from underneath. Look at that crack as it opens and closes. Look at that. Those displacements are huge as liquefaction is taking place. More water is coming to the surface, and very soon you're going to see these jets coming up. Look at those jets, and there's going to be more jets over here in a second. Look at that. All of those are jets of this pressure building up underneath that can't go anywhere but up, and that's essentially liquefaction. Very, very scary when you're there. I don't know how this guy actually took that video. I would be running if I were. I guess he's not a soil mechanician, so he doesn't know. Doesn't know better. So the other part where these materials are of importance is in the energy equation, which is perhaps one of the most important issues that we have today. So this is a pie chart that I stole from DOE. This is a pie chart of our energy sources today in the world. 85% of our sources, when you add coal, oil, and gas, come from some sort of granular material, essentially sands or soils and rocks. So 85% of our energy comes from these materials. On top of that, some of the most important new technologies that we're developing to extract more energy, like hydraulic fracture and CO2 geologic sequestration, are again related to these granular materials. Our ability to inject fluids or to eject or extract fluids from these materials is essential for our survival. Okay? So these materials play an enormous role in the energy question that we need to answer in our lifetime. Then they have to do with natural disasters also, like landslides. We're going to talk about landslides today. We're going to have some fun with landslides that we create in the laboratory in order to understand this kind of phenomenon. And again, here you see these very interesting transitions from a solid state to a fluid state. Look at that fingering. That's Venezuela during the El Nino season. You see this huge fingering effect. This is Taiwan, okay? And you see the interaction of this with infrastructure. Finally, we're going to take things out of this world and we're going to go to Mars, and we're going to actually look at how these materials affect planetary science. This is Curiosity, and that's a self-portrait of our latest rover on Mars. And we're going to learn how this mechanical geologist, essentially this robot, has to interact with granular materials in order to accomplish the science mission. Okay, so I think we got that granular materials are important. In fact, they're the second most manipulated material after water. So they're everywhere. They're in your pills, they're in your cereal. You can't avoid them. So in order to understand these materials, you need to develop paradigms, essentially tools that allow you to simulate their behavior and understand their behavior by looking at them. So we're going to, this is perhaps my only slide with equations. I apologize, I couldn't resist. I'm sorry. So we're going to study their behavior from 2 points of view. One point of view is going to be what we call the grain scale. This is the individualistic scale. We look at each grain and how it interacts with each other. We're very much interested in a grain, in this case, grain X and its neighbors. And we use what's called Newtonian mechanics, or Newton's second law, F equals ma, to describe this. And again, the procedure here is discrete. We look at each particle at a time, and our main concept here is going to be force. Okay? And we're going to define what force is in a minute. Then we take a jump to the large scale. Here, we no longer care about the individuals. We care about the collective. This is the socialist approach. Okay. Continuum mechanics is the name of this in our field. And this is a similar statement to F equals ma, but it's looking at the bulk. Okay? Here, it's saying that the stresses inside the bulk must balance the outside boundary conditions and the accelerations that they induce. Okay? Again, the average here and the bulk is what's important, and the main concept here is stress. It's no longer force. And we're going to learn what force and stress have in common. So in order to do this, I want to tell you a story, essentially, of how we got there. So let's start our story, and that story starts with Newton and Hooke. They're arch enemies, by the way. They really did not like each other. So I don't know what they would think if they knew that they're on the same slide now, but they both contributed to the concept of force. Newton said force equals mass times acceleration, meaning the force relates to a change in momentum, or relates to momentum. Hooke, on the other hand, thought more about the spring concept of force, right? We've all played with springs or with rubber bands, and we know that in order to stretch it, you need to apply force, right? So force relates to a deformation or a stretching delta via some material property, stiffness, K. And because he had enemies like Newton, he concealed his discovery in this anagram, just like it's written here. So who wants to take a crack at that? Tell me what that means. So in order to find that out, you need to speak Latin, okay? And you discover that that means utensio sic vis, and good luck with that one too, because I don't know Latin myself, but this means to the extension, so the force, or to the deformation, so the force. So that's the concept of force. So it has to do with deformation or with rigid body translations. After we got the concept of force down, this discrete framework, we went into this more average type of concept, and Cauchy made a huge contribution by introducing this concept of stress, right? By saying that force essentially, or stress is force divided by the area over which you're applying that force. So stress is the applied force over the area, right? So in a little bar that has a cross-sectional area A, the stress is the force that you apply, perhaps at the end of the bar, divided by the cross-sectional area. That's the stress. That's the concept of stress. So it's an average quantity. Remember, force is a discrete concept. Great. So once we understand stresses, then we are able to understand failure, because failure is related to stresses. So granular materials, or frictional materials, fail by what's called Mohr-Coulomb failure criterion, essentially the sliding block model. You have a block, right, and it's resting on a rough surface, and we all know that in order to slide the block, we need to apply enough force S, right, in order to make it slide that is greater than, say, the normal force times the frictional coefficient between the block and the rough surface, right? So essentially, we can define now a shear stress, which is the force, the horizontal force S, divided by the contact area A, shear stress. Normal stress, sigma, is the normal force divided by the contact area. So we can say that with enough shear, we can apply as much shear as we want, so long as we have enough normal stress times this friction coefficient mu. And this is a very important property in granular materials. This is called the friction coefficient, and it controls how much shear stress they can take. So when things are flowing, say under liquefaction, that's because tau has exceeded the amount of friction times the normal stress. So shear is related or proportional to pressure. Then came Terzaghi, and he's considered the father of soil mechanics, and introduces to this idea that these materials have fluids in between them, and this makes a big difference. So when I apply a stress on a matrix, which is a mixture of solid grains, let's say sands, and water in between them, this load is shared by the skeleton, the dry material, the sand itself, and the fluid. Now, this share, as anything in life, is not necessarily fair. Sometimes the skeleton takes more, sometimes the fluid takes more. It's not necessarily 50-50. But between the two of them, they need to add up to 100%. And not only that, this effective stress controls the deformation properties of these materials. So the deformation of the materials doesn't necessarily depend on the total stress, but really the effective stress, the stress that's being carried by the grains, if you will. Okay, then in 1968, we started learning more and more, and we developed mathematical models that enabled us to capture very complex behaviors. So this is an experiment where a group of sands, sand grains, is being compressed vertically as we're applying pressure horizontally. And we do two experiments, dense sand, so densely packed, and loose sand. And we see two very different, two things that are striking. First, if we plot the stress, so the amount of stress that the material can take, the dense material can take more than the loose material. So the dense material is stronger. We know that. The more we compact something, the stronger it usually is, right, when it comes to sand. But this is very striking, and perhaps you don't know this. The more dense the material is, the more it wants to dilate or gain in volume, whereas the loose material wants to contract. Okay, very different behaviors, and these two behaviors are connected. So density in these materials, pressure in these materials, makes a huge difference, and this is very different from all other engineering materials that we know about. And deformation in these materials is nonlinear and non-elastic. Caltech played a huge role also in the development of this field. And that comes from our own Ron Scott. And what Ron Scott has provided to myself and my students is essentially inspiration to go way out there and do things like nobody else is doing, essentially Caltech style. And he introduces to this concept that regolith, or extraterrestrial soil mechanics, was essential for planetary science when no one else was doing this. This is a picture of a Surveyor 3 mission where he designed and operated a scoop that was essentially scooping lunar soil. And he really redefined the field because he really took it literally out of this world. All right, then came 1979. And two things happened in 1979 that are very important to us tonight. The first one was the introduction of a paper that uses Newton's law, F equals ma, to simulate the behavior of this granular material. So we were able now, for the first time, to do computer simulations of this interaction of grains, just like the little movie I just showed, just to do a computer simulation of how they interact. The discrete element method was born in 1979. But then I was born in 1979. And I think it's fair to say that if this didn't happen, we wouldn't be here tonight. Just saying. So I hope I've convinced you that research takes a long time, and it builds one on top of the other. One concept leads to the other. So science evolves in time, and it's all about people. And without any of these contributions, we wouldn't be here today. So we know now the history of this field and where we are. So let's see what we can do with these paradigms and how we're pushing the envelope here at Caltech with the new techniques that we're developing to push on these paradigms. So I'm going to show you this by applications. And first, we're going to take it out of our planet. We're going to take a tour to Mars, let's say, and we're going to see how we apply these tools to do planetary science. So the first thing we do is we define our motivation. So NASA wants to do more in situ exploration. So we actually want to go places and actually touch these places as opposed to watching them from afar. Science that we do in situ relies a lot on understanding these materials, characterizing them, and also modeling them. This regolith is essentially, you can call it an extraterrestrial soil. It's soil, rock, or ice. It's the skin of these celestial bodies or these planets. And central to the mission of Mars are two celestial bodies. One is Mars and the other one is Europa, and I'm going to tell you a little bit about both. Why is Mars interesting? It's interesting because it has a very complex geologic process. It has had a lot of impact, a lot of landslides, gully formation, a lot of winds transporting granular materials from one part to the other. This is important because it encodes all of these processes that transform the surface of this planet, encode climate change, what happened to Mars, right? So Mars has very little atmosphere, and what happened to that atmosphere? How did it change? It's all encoded in the morphology, the surface of this planet. So science, the science quest is to determine the processes that modify the Martian crust. And the goal here is to eventually return a sample to core something, to take something and send it back to Earth. Europa is interesting because it's farther to Earth, and it displays very interesting features. This is an actual picture of Europa, a moon of Jupiter. And these lines here are called linea, and they're actually cracks. The surface of this moon is made out of ice, and these are cracks on that ice surface. And it's believed that this is induced by stresses that are generated by the gravitational forces exerted by Jupiter on Europa. So this moon is important because scientists believe that there's an ocean underneath this surface of ice. And this is a beautiful example of the linkage between mechanics and planetary science and how important it is to understand mechanics to unravel the science that we need to do. Great, so if we're gonna send a rover or something to interact with Mars or Europa, first we need to land, then we need to traverse, we need to go somewhere to do our science. Many times we have to penetrate or drill, and we also have to take samples. And all of these are interactions with these granular materials. So understanding the interaction with the sand or the ice between that and the rover is extremely important to our science. So in order to do this, we develop mathematical models, simulation models, that take us all the way from a grain, hopefully, to the rover. So in the next minutes, I'm going to show you how we go from the grain scale all the way to the engineering scale in order to do modeling and simulations of this material. So we're going to start getting deeper into the pushing the envelope, the tools that are being developed for this particular application. And of course, I'm not going to focus on the characterization or the experimental work, but there's also a heavy amount of work taking place here that is very important. I'm going to focus mostly on the modeling or the simulation part. So let's start at the shape, or at the grain scale, millimeter scale roughly. How many of you like the Black Eyed Peas? Not many? Okay. So this is the cover of the Black Eyed Peas, the End album. And I like it because it reminds me of a kind of work that we're doing. This is not a picture of a human being. It's actually a computer rendering of a picture, which is kind of a subtle difference. So this reminds me of this concept of an avatar. Okay, so let's define an avatar. We've probably seen the movie. The avatar is a computer simulation of an actual human being. And that computer simulation, what it does is it tries to represent the physical features. So it has to look like me, and it also has to behave like me. Okay? That's an avatar, but it's a computer simulation. For grains, you can do the same thing. You can have a mathematical representation of a grain of sand that represents the shape or the morphology of these grains, but also captures the behavior. And this is encoded in the kinematics and the forces. Remember Newton's second law, F equals ma. That's everything for these materials. That represents their behavior. So we're going to introduce avatars for these granular materials that have to capture morphology and behavior accurately. And we're going to do this by computer simulation. But before we do that, we need to measure how these materials actually behave in the laboratory. So this is a sample of sand that is sitting, it's very small, it's about 2 centimeters high by 1 centimeter in diameter. It's being squeezed under a chamber that is under pressure. So it's being squeezed axially along the axis, and X-rays are being shot as this is happening. So this is a slice, this is just a slice of that sample. And what you see here is this shape of grains that is essentially a picture taken by X-rays. It's a tomographic picture. So we like to go from a picture, so remember the avatar concept, from a picture or an image of the actual thing all the way to the avatar. And here's the avatar using level sets, essentially mathematical representations of reality. So here's the actual grain coming from the X-ray. Here is its avatar, which is a mathematical representation of that shape. What do we do with that? Well, we can use that to then be able to measure the translation and rotations of every single grain, actually, inside of this sample. And there are thousands of grains. And we can do this for relatively large samples in a very, very accurate way. So we're able to measure or experimentally capture not only the shape, the morphology, but also how these grains move. But that's only half the story. Remember that behavior also depends on force. So to do that, and remember force chains, way at the beginning of this lecture, we looked at this technique called photoelasticity, right? Where we see these grains lighting up as they carry load. This can only be applied to birefringent materials, so transparent materials that shine when they're loaded. But for instance, you cannot apply it to sand or to sugar that is non-transparent. So we've developed a method called the granular element method that can be used with any material that is not necessarily transparent, say sand. As long as we have an image source, say an X-ray machine, or even take pictures from the surface, we're able to feed this information through image correlation techniques and this framework developed by Newtonian mechanics and continuum mechanics, these equations that we saw from Newton and Cauchy, to eventually lead to every single interparticle force, or the forces that each particle is sharing with every single neighbor in any material. So we're able to experimentally capture these interparticle forces without having to rely on photoelasticity, combining, again, these experiments with computational tools using mathematics. So now we're able to measure, essentially, these guys have no privacy anymore, essentially. We can watch them everywhere, right? We know how they look like, and we can follow them. We know their steps, and we can also measure their forces everywhere. That's great for understanding, but that's not predictive yet. So you can take it one step further and try to predict by developing a computational avatar. So the computational avatar is very similar to the experimental avatar, if you will. It tries to capture the morphology. So this is a this is an X-ray picture of an actual grain of sand. And this is its avatar counterpart. This is a mathematical representation of that grain using a technology called NURBS, or non-uniform rational B-splines. So we can get, with these techniques, we can get the shape of these guys. But that's not enough. Then we use Newtonian mechanics and the concepts introduced by Hooke, forces related to deformations, to actually predict the kinematics, the way that these guys move as a function of the formation, but also to compute their forces. So with this technique, we can simulate now and predict the behavior of this material. So we can measure it in the laboratory, but we can actually go ahead and predict it and then compare the two and see how we do. But that's still at the very small scale. We want to go here. We want to go very large. So we need to make a jump in scales, right? At least by 2 orders or 3. So, and the issue is that here's our reality, right? And we have the avatar at the grain scale. And this is our current modeling techniques, which are very Mickey Mouse-like, to be honest. So we're still not very sophisticated at this scale. So we want to really improve here. And the idea is to infuse concepts from the avatar, these granular interactions, to the large scale. And the challenge is how to do that, and how to fill this gap between reality and a computer simulation of reality. So again, you're going to start to see a trend here. We go back to an experiment. This takes place at MIT. This is a wheel crawling on top of a Martian soil simulant. And what we're learning here is the interaction between this wheel and this Martian soil underneath. And I'm going to show you a video of what that looks like. So here's the wheel crawling on top, and you're going to see this band that forms here. And that band is called a shear band or a failure zone It's the part where the sand fails. Remember, shear is too high there. It's greater than the coefficient of friction times the normal force. So this area of intense deformation forms. What's neat about this video that you might not know is that here we're superimposing a computational model on top of the actual video. So the thing in gray in the background, it's actually an image, a picture in the lab. The mesh that you see here in color is a computational mesh, and it's taking data from the lab to inject into this computational model and actually start to make predictions of how things are going to evolve. So this is a very intimate relation between experiments and computation like never before in our field. So in order to do this, to make this marriage or this match between the experiments and computation, so we want to go here to our computational model to predict this shear band. We need to extract information from the experiment. And remember dilatancy, that property that we described when you walk on sand? So we're measuring exactly that in the lab. We are able to use digital image correlation to keep track of these grains and eventually compute how they dilate, how they develop dilation in the laboratory as the wheel. Now it's no longer a guy walking on the beach. It's now the wheel that is crawling on top of this soil is still shearing it or deforming it, and that creates dilatancy. And we measure that and then inject that into our model to make predictions. So we take information directly from the experiments to make computations and simulations. Great. So we've looked at applications outside of our planet. Now let's take a look at something closer to us. Let's look at landslides that actually happen here on Earth. So the first thing I'm going to show you is a video, and here I want to play the audio because I think that the audio is very telling. You're going to see an actual video of a landslide that occurs in Italy, and you see how intense it gets. That's a landslide. It's not a river. It's actually soil rushing down. The mountain is essentially melting. I think you got that. Okay, so so you see these very sharp transitions from something that is very solid-like a mountain, and all of a sudden these landslides that start just melting this, and the scale here is huge. So this transition from solid state to fluid state is a serious business, and it's very difficult to model computationally. So we want to make the jump from solid state, say a sand dune, just sitting there, chilling, to a landslide, right? Something that behaves very much like a fluid that even has fingering effects. So we have a missing link here in our paradigm or in our way of simulating things. We're very good at simulating this or simulating that, but we cannot really transition very well. So again, you're going to see the same theme that you saw before for Martian or planetary science applications. It's this combination of tools or approaches. So we're going to use experiments, simulations, and theory to essentially decode what we call the life cycle of an avalanche. An avalanche has a birth, it has a peak, and eventually it has a death. And we want to understand what controls those stages from a mechanical point of view. So let's start with experiments, what we see in the laboratory. So here at Caltech, we have bench top avalanches. So this is a drum. It's called a rotating drum. It's relatively thin. It's about 1 inch in depth, if you will. And it has a much larger diameter, and it's half full, as you can see, with steel beads. And those steel beads are very small. They're about 1 millimeter in diameter. And what we do with this drum is we rotated it with a constant angular velocity that is very small, about 1 rotation per day, tiny, okay? And then we take pictures of it with a very high fidelity camera, and we watch every grain as it rushes down to understand these avalanches. So here's a video of that. As it's rotating this way, the drum, you see an avalanche born and die. And then, as anything in life, the cycle repeats, right? When somebody dies, someone else is born. Right? So the same happens with the avalanches. You have an avalanche, it's born, it dies, a new one comes afterwards if you keep rotating this drum. What makes these avalanches rush down at that angle? So this is called the angle of inclination. So these avalanches are able, the drum is able to climb to a very steep angle. Then an avalanche is formed, and if you notice very carefully, the angle is lower at rest or at death. At the death time of the avalanche, the resting angle is actually lower than the avalanche angle. Sorry, so let me go back. Here. So these are snapshots of what you just saw. So here at A, nothing is happening, and we keep rotating the drum, right, increasing this angle of inclination, until eventually we reach a point where an avalanche is born. Here, all the grains start rushing down. By the time we're at D, you have an avalanche, and then eventually things quiet down. The point is that there's a big difference, about 10 degrees, between the angle at which the avalanche is born and the angle at which the avalanche dies. And what puzzles people is what controls that difference. Okay? So to be able to look further into this, we develop supercomputer simulations using this technique called the discrete element method. Remember, that method that was born in 1979. So here's a supercomputer simulation with thousands of grains doing exactly the same experiment that you just saw, rotating that drum, and eventually you're going to see an avalanche forming up here. The color here is velocity. So you see the grains rushing down. This is a group of grains that used to be together and now are rushing down. And this is the same angle of inclination as it peaks and then it rests, just as in the experiment. So this is how the simulations, the avatar, if you will, compares to the experiment. So we're comparing simulation in blue to the experiment, and we're plotting the angle of inclination, so as the avalanche occurs, and then rest, and you see that they're essentially one on top of the other. And then you see the surface velocity, so the velocity at the top of the flowing layer. You see it beginning at 0, then peaking and going down, and essentially the trend is the same. So the computer simulation is able to reproduce the behavior quite well. But this requires a supercomputer and enormous amount of resources. We want to develop a theory that is much cheaper and can actually give us further insight. And we're going to use this concept that we introduced before, this concept of shear stress related to normal stress. And remember those plasticity models that we introduced in 1968? We're pushing the envelope on those to actually develop theories, models, mathematical models, that can do exactly the same thing as these supercomputer simulations. So here in dots are those supercomputer simulations that I showed you before, this angle of inclination. And in the solid line, it's a prediction from the theory. So you see that the theory is matching the simulation, the supercomputer simulation, very well. The solid line takes seconds to run. The dotted line takes days, if not weeks. But the more important thing is the comparison with experiments, with actual reality. And you see that the solid line here, again, the angle of inclination for the life cycle of the avalanche. The red line is the theory. The green dots, the green X's, are the experimental data, and the model essentially matches the experiment quite well. So our theory is able to reproduce the experiments fairly accurately. Great. So I'm getting towards the end of my talk, and I want to, again, emphasize this idea that research doesn't happen in a vacuum, and it's really an effort that requires a lot of people. Okay, so I want to end, before I end, I want to acknowledge the people that we work here at Caltech, but also people we work with around the globe. And this is an incomplete list of people that we work with and have fun with. Great. So that brings me to my closure, and I really want to emphasize essentially 3 points. That is that these materials, these granular materials that we have studied today and have fun with, hopefully, are very puzzling. They're very neat. They're very cute. But they're not only that, they're also very important. They matter for a lot of things, a lot of processes that take place here on Earth and also outside of our planet. And I also want you to leave this room or this auditorium knowing that here at Caltech, we're pushing the envelope on these techniques that allow us essentially to simulate the behavior, and hopefully one day they will allow us to predict some of the issues that we have discussed tonight. With that, I want to thank you very much for coming, and I'll be happy to take questions. Thank you.